Hello, and thank you for joining me in this video where we're going to be taking a look at the Gaussian integral. Now, I'm not going to be using the polar coordinates way of solving the Gaussian integral, but I'm going to be showing you guys a really elegant and beautiful method using the Feynman technique, which is also known as differentiation under the integral sign. So let's not waste any time and let's get right into it. Alright, so this is the Gaussian integral right here. Alright, and because e to the minus x squared is an even function, we can say that this is equal to 2 lots of the integral from 0 to infinity of e to the minus x squared dx. Now, I just said it's an even function, but what does that actually mean? Well, if we take a look at the graph of e to the minus x squared, which looks something like this, what you notice is that the area on the left hand side of the y-axis and the right hand side of the y-axis is the same. So taking the integral from negative infinity to infinity is the same as taking the integral from 0 to infinity and just doubling that. Alright, that's all we mean when we say it's an even function. It's symmetric about the y-axis. Alright, so to begin with, let me define a function f of t. And I'm going to say that it's the integral from 0 to infinity of e to the minus t squared times x squared plus 1, all of that divided by x squared plus 1 dx. Alright, so now we're going to calculate the derivative of f of t. Alright, what is that going to be? Well, it's going to be the partial derivative with respect to t of the integral from 0 to infinity of e to the minus t squared times x squared plus 1, all divided by x squared plus 1 dx. Alright, so what does the partial derivative mean? Well, it's used when you have more than one variable, and it's just to pinpoint one specific variable and differentiate with respect to that. And here, because we have the x and the t, we're just saying that we're going to be differentiating with respect to the t. And everything else can be considered as a constant. Alright, so let's evaluate that. So that's going to be equal to the integral from 0 to infinity. Well, this is just e to the power of a function. So we're going to have the e to the power of that same thing. And we're going to multiply that by the derivative of the function on the top, which is times minus 2t times x squared plus 1. All of that divided by x squared plus 1 dx. Alright, so what I did there was, if you're gonna find the derivative of e to the power of function of x, that's just equal to e to the power of function of x, which is that, multiplied by the derivative of function of x, which is that. And everything else just remains as it is, alright, because they're just a constant. Alright, so right off the bat, we notice that this and this just cancels out. Alright, I'm going to move the negative 2t outside. Alright, so I'm going to say this equals negative 2t times the integral from 0 to infinity of e to the minus t squared times x squared plus 1 dx. Alright, see how nicely we've differentiated this. So now I'm going to distribute the t squared throughout the power. Alright, so the top is going to become minus t squared x squared minus t squared. And now we can split up this into two different powers of e, or two different exponents. So let me change the color. So this bit is going to be equal to e to the minus t squared x squared times e to the minus t squared. These two are essentially the same thing, right? So we're just calculate the integral of this thing here from 0 to infinity minus 2t here dt. Alright, dx. Alright, now this term here doesn't have an x in it, so we can just move that outside, the e to the minus t squared. We can just move that outside. Alright, e to the minus t squared. Alright, nice. So we've reduced this integral down to this. Oh, sorry, this down to this. Alright, so let me clear up the whiteboard and let's move on. Alright, so we're in this stage now. So we've defined a f function of t and we've calculated the derivative of that function. Alright, or the partial derivative with respect to t. Alright, so what I'm going to do now is I'm going to do a quick u sub, alright, with this color, okay, u sub on this integral here. So what I'm going to do is I'm going to let sigma, because why not, equal to tx, alright, so d sigma is going to be equal to t times dx. Now because this is linear, the bounds are going to stay the same, because as x goes to 0, sigma is going to go to 0. As x goes to infinity, sigma is going to go to infinity. So bounds stay the same. So the integral transforms into the integral from 0 to infinity of e to the negative sigma squared times, so dx, if we rearrange this, it's going to be equal to 1 divided by t times d sigma, which is going to be 1 divided by t times d sigma. Alright, so this is dx. Cool. So we've transformed our integral here using a quick u sub. Alright, so I'm going to write the outside terms here as well. Alright, so one thing we notice is the t's cancel out. So let me just rub this out here. And there we go. This is very similar to this here, without the 2, unless you include this 2 here. But yeah, this is basically very similar to this, but it's got different variable. Now, the variable doesn't really matter. These two are essentially the same thing, but with different variables. So if I call this inside bit here, alright, excluding the 2, if I call that alpha, alright, this bit, so this thing is going to be equal to negative 2 e to the minus t squared alpha. Alright, so alpha is what we're essentially trying to calculate. Alright, so the derivative of f of t is equal to negative 2 e to the minus t squared alpha. Cool. So now we're just going to take the integral of both sides. So we're going to integrate the derivative of f of t from 0 to infinity dt, and we're going to integrate this thing here from 0 to infinity. So minus 2 e to the minus t squared dt times alpha. Now the alpha is outside because this thing here doesn't have anything to do with t. It doesn't have any variable t, so we can just move that outside and keep it outside. Now I'm going to take the negative 2 outside, and voila! How beautiful is that? We have alpha again, or the Gaussian, or shortened Gaussian integral again. How beautiful is that? Alright, so let's get rid of this here and substitute alpha into it. Alright, so alpha times alpha, which is alpha squared. We're going to have negative 2 alpha squared. Let me just write the negative 2 properly. Alright, so the integral from 0 to infinity of the derivative of f of t dt is equal to negative 2 alpha squared. Now, because of the fundamental theorem of calculus, we know that this thing here is equal to f of t calculated between 0 to infinity. Alright, so what is f of 0? Let's calculate that first. So that's the integral from 0 to infinity of e to the negative, 0, because if you put 0 for t, everything is just 0, divided by x squared plus 1 dx. Now the top, e to the negative 0, is just going to be 1. So we're finding this integral here, which is just the arctan of x evaluated between 0 to infinity, which is going to be arctan of infinity minus arctan of 0, which is just going to equal to pi over 2. Alright, so f of 0 is pi over 2. So let me rub this out here. Rub this out as well. So f of 0, we've just figured out, is pi over 2. So now we have to find f of infinity. Alright, So that's going to be the integral from 0 to infinity. Okay, so now if we have, so let's take this top function out here, alright? So let's analyze it. We have e to the negative t squared times x squared plus 1. Alright, so this thing, we can rewrite that as 1 divided by, well, e to the t squared x squared plus 1. Now, if we put infinity here instead of t, well, e to the power of infinity is going to be a very, very, very big number. Alright, so if we calculate the limit of this as t approaches infinity, that's just going to make the denominator very, very, very big. So which means this is going to just equal to 0. Alright, so the limit is just going to be 0. So if the top bit is 0, this whole thing goes down to 0 dx. Alright, so that's what we're going to be calculating now, 0 dx. Well, what is 0 dx? Well, if you have a look at the graph of x equals 0, which is just this, the x-axis basically, and the area underneath that is just 0. Okay, the area bounded between the x-axis and the x-axis, so itself, is 0. So the integral is just equal to 0. Alright, so with a bit of intuition, we found out that this is just 0. Alright, so this thing here is just equal to f of infinity minus f of 0. We know f of infinity, which is 0, minus, we know f of 0, which is pi over 2. Pi over 2, that's just minus pi over 2. Alright, cool. So we've just figured out that this integral here, derivative of f of t dt, is equal to negative pi over 2. So negative pi over 2 equals negative 2 alpha squared. So that means 2 alpha squared equals pi over 2. Alpha squared equals pi over 4. So that means alpha equals square root pi all divided by 2. Wonderful. Alright, so we know that alpha is equal to this thing here. But the Gaussian integral is actually equal to 2 lots of alpha. So 2 lots of alpha, let me change color for the grand reveal. 2 lots of alpha is equal to root pi over 2 times 2, which is equal to square root pi. And voila, there we go. This is the answer to the Gaussian integral. How beautiful was that? Thank you very much for watching this video, and please subscribe.